All right, we welcome you to our today's class. So we will be starting a new topic in engineering, which is thermodynamics relation. So we'll be going into the introductory part, which is fundamentals of partial differentiation. All right, so we are going to start with this concept, and this concept starts with this. We are going to assuming we have three variables, which are x, y, and z. These are three variables. Now, if we are to write the functional relationship between these three variables, this is how we are going to write it. F into x, y, z, everything equals to 0. So this is going to be the functional relationship between these three variables, of which we can write our s will be equals to x into y, z, and y will be equals to y into s, z, and z will be equals to z into x, y. So let's call this our equation 1, and this our equation 2, and this our equation 3. All right. Now, x here is known as the dependent variable. While everything we have here, they are all known as what? The independent variable. All right. So now, the next thing we are going to do is, if we take the differential of equation 1, what are we going to have? So if we differentiate equation 1, this is what we are going to have. So we are going to have the s to be equals to, it has to be equals to the partial differentiation of s in respect to the partial differentiation of y, keeping z constant, then the s, the y rather, y, plus the partial differentiation of s respect to the partial differentiation of z, keeping y constant, then the z. All right. So this equation that you are seeing here, it is known as an exact equation, especially this dx. But this equation itself is known as the differential equation. All right. Now, how do we know this? Now, this is what we are going to do. Next thing is, we are going to replace what is here with m, and I'm going to replace what is here with n. This will be replaced with m. This will be replaced with n. So we are going to say let m, let me write it here. Let m be equals to the partial differentiation of s in respect to the partial differentiation of y, keeping z constant, and n to be equals to the partial differentiation of s, partial differentiation of z, keeping y constant. Sorry, this is y. Don't know why it's not showing. All right. So now, the next thing we are going to do is, if we replace what is here with m and what is here with n, we can therefore rewrite this equation as the s to be equals to m dy. So this will be m dy plus n dz. All right, so let's keep this equation. All right, now, if I come here now, let's come and pick m. M is equals to the partial differentiation of s respect to the partial differentiation of y, keeping z constant. We are keeping z constant. All right, and n is equals to the partial differentiation of s, partial derivative of s, respect to the partial derivative of z, keeping y constant. All right, if I differentiate will I get? So I'm going to differentiate this. The partial derivative of m in respect to the partial derivative of z will be equals to, now we are differentiating this, so we are going to have this as derivative of this in respect to z, then into everything that we have there, which is the s, all over what? The y. So if we do this now, our dm in respect to the partial derivative of z will be equals to this multiplied by this is going to give us square s all over dz, then dy. All right. So what we did here, let's apply it to n as well. So we are going to say the partial derivative of n in respect to, we are going to differentiate in respect to y. In respect to the partial derivative of y will be equals to partial derivative all over the partial derivative of y into the s, that is the partial derivative of s, with respect to the partial derivative of z, keeping y constant. All right, so this multiplied by this is going to give us this, the partial derivative of n all over the partial derivative of y is going to be equals to square, that is the partial square, then s plus this square s all over the y, then the z. All right, so now you can see that this equation here, let's call this equation number 4, and let's call this equation 5. All right, you can see that equation 4 and equation 5, they are the same thing. We have the same result here and the same result here. So we can equate equation 4 to be equals to equation 5. So we can therefore say del m all over del z is equals to partial derivative of n all over the partial derivative of y. So this is called an exact differential equation. So this is called an exact differential equation. All right. So this is how, you know, from here I already said this equation here is a differential. Sorry, this equation here is called an exact. So this is what I did here is just to show you why it is exact. Is that clear? All right. So now the next thing we are going to do is we are going to apply the way we write this equation here. We are going to apply the way we write this equation here. Then we are going to apply it to equation 2 and equation 3. So we want to write equation 2 and equation 3 in this form. All right. So now equation 2, we said y is equals to y into s comma what? Z. So if we differentiate this, we are going to have what? We are going to have the y to be equals to, that is partial derivative of y in respect to the partial derivative of s, keeping z constant, ds, plus the partial derivative of y in respect to the partial derivative of z, keeping s constant, dz. All right, so this is how we are going to write this. All right, so let's call this equation 6. Let's call this equation number 6. All right, so now let's rewrite equation 3 in this format as well. So we said z is equal to z into s comma y. So this is going to be giving us dz is equals to the partial derivative of z all over the partial derivative of s, keeping y constant, dz, plus the partial derivative of z in respect to the partial derivative of y, keeping s constant, dy. All right, so let's call this equation number 7. All right, so now the next thing we are going to do is this. We are going to substitute equation 7 into equation 6 since we are having the z here, and we said the z is equals to everything we have here. So now let's this one supposed to be the x. Sorry, just looking at it now. Supposed to be the x, not the z. All right. So now everything we are having here, we are going to substitute it here. So if we are going to do that, so let me rub up this part. Okay. So we are substituting this into that equation now. So we can therefore say the y will be equals to, we have the partial derivative of y respect to the partial derivative of s, the s, sorry, keeping z constant, the s plus the partial derivative of y all over the partial derivative of z, keeping s constant, the z. But we are not going to write the z now. We are going to write what is here. So here we are having it as the z all over what? The s, then keeping y constant, the s plus the partial derivative of z, keeping all over the partial derivative of y, keeping s constant, the y. So we can close the bracket now. All right. So this is what we are going to have. All right. Now the next thing is we are going to clear this bracket. All right. Please don't use this to multiply this bracket, or don't go and take this bracket like this. You get that? Don't go and put this in bracket and this in bracket, then by saying this multiply this, this multiply this, this multiply this. No, this is not going to be. This is the way it is. It means we are using only the term here to multiply this bracket. So this will multiply this will also multiply this. All right. So now we can therefore say the y is equals to partial derivative of y all over the partial derivative of s, keeping z constant, the s plus this multiply this is going to give us what? It's going to give us partial derivative of y all over the partial derivative of z, keeping s constant, into partial derivative of z all over the partial derivative of s, keeping y constant, that is the s, plus. So this will multiply this. We are going to have partial derivative of y all over the partial derivative of z, keeping s constant, into okay, please pardon, let me clean this part. All right. So now into partial derivative of z all over the partial derivative of y, all over the partial derivative of y, keeping s constant, that is the y. All right. So this is what we are going to have. All right. Now, if you look at this, we are having s here, right? Now it means we can merge what is here together. That is what it meant. All right. So we can therefore say the y is equals to partial derivative of y all over the partial derivative of s, keeping z constant, the s, plus partial derivative of y all over the partial derivative of z, keeping s constant, into the partial derivative of z all over the partial derivative of s, keeping y constant, the s. All right. Now, if you look at this, we can make them together. That is, let me make them together. I don't want to jump steps. I would have loved to jump steps, but I will not do that. All right. So now we open this bracket. We are going to have plus into. So this is going to be partial derivative of y all over partial derivative of z multiplied by partial derivative of z all over the partial derivative of y into s dy. So what do you notice? What do we notice here? We notice that The y will cancel out the y, and partial derivative of z will cancel out partial derivative of z. So this will neutralize this will neutralize this. So we're left with 1, and 1 multiplied by the y is nothing but what? The y. So now we can therefore write this equation as the y equals to partial derivative of y all over partial derivative of s, keeping z constant, the s, plus partial derivative of y all over the partial derivative of z, keeping s constant, in partial derivative of z all over the partial derivative of s, keeping y constant, the s, plus what? The y. All right. What do you notice here? We notice here that the y here will cancel out the y here. So therefore, this equation now will be equated to what? 0. All right. Now, means that now, so let me explain this further. If I bring this dy that is here to this other side, it's going to change to what? Minus dy. So we are going to have dy minus dy, which is what? 0. Because you might be finding it hard to understand. That's why I emphasize on that. Take note of that. So now we are going to be left with the y, partial derivative of y, all over the partial derivative of s, keeping z constant, the s plus the partial derivative of z, of y, keeping over partial derivative of z, keeping s constant, into the partial derivative of z all over the partial derivative of s, keeping y constant, the s, everything equals to what? 0. Everything equals to 0. All right, so now we are having the s to be common here. So if we divide through by the s, you can factor out the s, or you divide through by the s. Okay, we factor out the s, we'll be left with the y all over the s, keeping z constant, plus partial derivative of y all over the partial derivative of z, keeping s constant, into the partial derivative of z all over the partial derivative of s, keeping y constant. So if I factor out the s, I'm going to put this in brackets, then everything equals to 0. All right. Now, the next thing is I'm going to divide through by the s. So if I divide both sides by the s, I'll also divide 0 by the s. So this ds will cancel out this ds here. And 0 divided by the s is still what? 0. So it means this equation will become partial derivative of y all over the partial derivative of x, keeping z constant, plus the partial derivative of y all over the partial derivative of z, keeping s constant, into the partial derivative of z all over the partial derivative of s, keeping y constant, equals to what? 0. All right. Now, the next thing we want to do is this. Now, I can move what is here to this other side. If I move what is here to this other side, it's going to change to what? Negative. So we'll be having 0 minus what is here, which is going to give us what? Negative of this answer. All right. So now we are going to say the partial derivative of y all over the partial derivative of z, keeping s constant, into the partial derivative of z all over the partial derivative of s, keeping y constant, is going to be equals to 0 minus the partial derivative of y all over the partial derivative of s, keeping z constant. So 0 minus what is here is going to give us the negative of this. So there's no big deal in that. So let me just clean it and write the result direct. So we are going to have negative of the partial derivative of y all over the partial derivative of s, keeping z constant. All right. Now we are having a negative sign here. All right. Now, I want to cancel out this part. I want what is here to come back here in form of multiplication. How will I do that? All right. So for me to do that, I am going to divide both sides by uh, I'm going to divide both sides by the y all over what? The s. In respect to what? S. If I do that, this is what is going to happen. Let me clean this part. All right. So let's divide both sides now. If I divide both sides by the y all over partial derivative of s, keeping z constant, all over partial derivative of y all over partial derivative of s, keeping z constant. So this we cancel out this. We left with minus 1 here. So let me rewrite everything that is here. Now, let me rewrite it here. So we are going to have partial derivative of y all over the partial derivative of z, keeping s constant, into partial derivative of z all over the partial derivative of s, keeping y constant, all over partial derivative of y all over the partial derivative of s, keeping z constant, everything equals to what? Sorry, minus 1. All right. Now, if I want to let what is here to come back up, what will I do? I will just take this up and bring this down. Then it means this is going to be what? It's going to be ds all over what? The y. Keeping z constant into dy. Sorry, partial derivative rather. This is partial, please. Partial derivative of y all over the partial derivative of z, keeping s constant, into the partial derivative of z all over the partial derivative of s, keeping y constant, is equal to what? Minus 1. All right. So let's arrange this properly. Let's arrange it properly. Let z come first and y follow and s. So we are going to have this as partial derivative of s all over the partial derivative of y, keeping z constant, into partial derivative of z all over the partial derivative of s, keeping y constant, into the partial derivative of y all over the partial derivative of z, keeping s constant, equals to what? Minus 1. All right. Now let's write what is here in form of PVT. P, V, and T. All right. Now for us to do that, it means this one here is s, this one here is y, and this one here is z. So let's replace s. Anywhere we see s in this equation here, replace it with p. Anywhere we see y, we replace it with b. Anywhere we see z, we replace it with what? T. All right. So let's do that. So here we are going to have partial derivative of s. What is s here? Which is p. It's going to be partial derivative of p all over partial derivative of y, which is what? V. Then keeping z constant, z is what? T. Then into partial derivative of z. What is z? T. So it's going to be partial derivative of t, partial derivative of t all over partial derivative of t all over. So it's going to be partial derivative of t, partial derivative of t all over partial derivative of s, but our s is p, partial derivative of p, keeping y constant, but our y here is what? V. So it's going to be v into partial derivative of y. Y is what? V. Partial derivative of v all over the partial derivative of z. Z is t. Partial derivative of t, keeping s constant, but s is what? P. S is P. So this is P, which is equal to what? Minus 1. All right. So this equation here is being referred to as what? Cyclic relation. Relating what? It's relating temperature, pressure, and volume. So this equation will be used for our further learning as we proceed in this topic. All right, so stay tuned for our next topic, which is going to be derivation of Maxwell relation. Thanks.